Hi, this is Sanjay Gangal from EDA Cafe. I'm here with Richard Depoto, Business Development Manager at Uyemura International. Hello, Richard.
Hello, how are you? Good morning. Good
Uh,
afternoon.
well, good morning and good afternoon. You are on East Coast, I'm on West Coast, USA. Richard, tell us about Uyemura International.
Well, the Umura Corporation is about a $500 million world global company. Company is 170 years old, so it's a very, very old company. And it's been in the plating chemistry field, specifically working on specialty chemicals for over 60 years. It prides itself in focusing specifically on specialty plating chemicals.
Okay.
And so it has a core business that it is passionate about and has stayed true to that and worked very hard in establishing the highest level of technology in that field. Uyemura International is the division in the United States. It services North America. It specializes specifically in final finish chemistries for the electronics industry. The electronics industry that we service in a big way is the printed circuit industry, the semiconductor industry, as well as that space between ICs and PCBs, which is called sometimes microelectronics, but most recently has been called the additive part of the market.
And what are the latest market trends you are seeing in this space?
Well, the biggest trend that we see specifically in the printed circuit market, which is our largest share market, is that as assembly processes get more and more complex, one of the finishes that has a large market share is ENIG, and we're beginning to see a conversion from ENIG over to what we call ENEPIG. ENIG is electroless nickel, immersion gold, and ENEPIG is the use of a palladium layer in between the nickel and the gold. And specifically what's driving that is as circuits require more reliability, and as those assembly processes get more complex, they need a finish which is more robust to solderability and preserves solderability for a longer time. So that the use of the palladium, another precious metal in that layer deposit, really gives high reliability applications a big edge.
Okay.
And
you're also seeing a much higher frequency designs and requirements for the high frequency designs as well?
Yeah, there are really three operating, drivers that are going on. High voltage, specifically for automotive, that's a major one. Higher mechanical stress, and the one that we see across the board as RF technology increases dramatically is the need for higher and higher frequencies. You know, we constantly look at hockey stick curves and we say, oh my gosh, that's an overplay. It's going to take a lot longer to get there. I can tell you that in the high frequency market, that hockey stick of frequency change has, if anything, it's accelerated. And so where, we thought that we might be operating in the 10 gig and 8 gig range for a while, and that would suffice. The 5G is coming on board faster than we ever thought, and new designs are continually pushing 25 gig and even as high as 75 gig, which normally had been reserved for military and radar applications. And so that has put a tremendous design stress, a bit of a disruption on designers trying to design circuits, faster than the manufacturing technology is really ready. And so that's an area that we've been working very heavily on.
And what specifically is Uyemura's strength in this high frequency area?
Sure. Sure. We have two basic strengths related specifically to our core competencies. Basically, there's three things that can help on high frequency. One is the materials themselves, what we call the substrates or the laminates. We are not involved in that part, but many companies are working on that. The parts that we are involved in are the copper traces themselves, and specifically the surface finishes. High frequency circuits require a very low profile copper without roughness, much like as if you're moving on a sheet of ice. The electrons want to move on a very smooth surface rather than a roughened surface. And so producing traces which have low roughness is a very important thing. A lot of our and most recent efforts and our core competency that I've mentioned is surface finishes. Electroless nickel immersion gold has many advantages and has been the preferred finish for a long time in high rel applications. The problem with electroless nickel immersion gold is that nickel is magnetic. If there's any magnetic effects, an interference occurs on the signal, and so the elimination of nickel from the surface finish is very important. The choice in order to eliminate it is palladium, and so we've come up with non-nickel finishes that still preserve ENIG solderability capability, but remove that magnetic property of nickel.
Yeah. And is there an increasing need for higher gold thickness as well in some of the applications?
There are. As we move away in the assembly process, away towards solderless connections and the elimination of soldering, we have a lot more press fit and hydrostatic pogo pin assemblies where there's no soldering involved. In that case, the reliability of those press or hydrostatic components is enhanced greatly if we can put down thicker gold. Now, thicker gold is a difficult process to do. Requires an electroless or a reduction-assisted gold process, which is different than what's been out there. It's an area that we specialize in. We were the early adopters of electroless golds, and so we have by far the largest portfolio of thick gold electroless processes, and they're gaining a lot of traction as these assembly processes get more complex.
Okay, and are you seeing a lot more need for additive processes versus subtractive processes that have been used in the past for both PCBs and ICs?
Absolutely. Everybody wondered at what point would a subtractive process, begin to, be too difficult to achieve. And then when, and subtractive has done a great job extending its life significantly. And for the great majority of the products in PCBs, it is used, extensively. However, the next level, the next generation, which is coming on quicker, requires additive processes. Right now, we see those processes coming in that gray area between PCBs and semiconductors. We call that particular market microelectronics or an additive market where metals and metal deposition is additive. It is a increasingly great option for MEM devices, for the use of sensors and multi-chip modules that are being designed at a very rapid rate in this market. We have been involved in additive for a long time, and it looks like the portfolio that we have and the one that we're developing is going to fit really nicely with that market.
Okay. Now, many of these processes, chemical processes, can be toxic to the environment. Can you tell us about any of your sustainability initiatives?
Sure. We're always conscious of that. We do that very strongly through our OEM programs. Many of the OEMs or sort of running ahead of the manufacturers and asking and make sure that they have sustainability. And so we work with a lot of OEMs specifically on things. We are asked, we have programs which are reducing the amount of cyanide, which is one of the more popular complexers of gold solutions. So the elimination of cyanide is one of the processes that we brought to market and that we have available. This is particularly interesting and important for the semiconductor applications. The other one is formaldehyde. That's an area that people want to work on, and so we've worked on reducing the use and the need for formaldehyde, which is a very important reducing agent for a lot of these electrolytes.
Earlier on, you touched upon some requirements for automotive as well. So tell us what are the automotive requirements, and how is Uyemura's processes supporting that?
Sure. Well, here's the situation. I mean, although the internal combustion engine is an amazing invention and does really a very efficient job of things, many estimates show that by 2030, both hybrid vehicles and fully electric cars are predicted to be about 30 to 40% of the market. And what that brings are three levels of challenges to occur. The first one's obvious, and that's the fact that 12-volt systems in hybrids will move to 48, and then in fully electronic vehicles, the demands for voltage will be 1,000 volts. No one is going to be happy unless their car can charge in less than an hour and maybe even 15 minutes. When you're putting 1,000 volts through circuit designs, that is an area of design reliability that is new. And so that's a particular area that will need to be addressed with new alloys, with new corrosion-resistant materials. All of these are wet processes in the presence of water at 1,000 volts. That's quite a different situation than a 12-volt system. And so there's going to be a lot of work on reducing ionic contamination, moisture, and improving corrosion resistance as these vehicles get on the market. The second part has to do with higher frequencies. Everybody realizes in the Internet of Things that autonomous vehicles are going to use RF signal processes. So we expect many of these vehicles to be operating with electrical designs in the 50 to 7, even the 70 gigahertz range, which has been touched by 5G requirements. And so all of the things I talked about on the surface finish side related to addressing high frequency surface finishes are all going to come into play.
Okay. And what is the best way for people to find out more about Uyemura on the internet?
Yeah, we have a very extensive website that we're very proud of. That is www.uyemura.com. Again, that Uyemura is spelled Uyemura. So www.uyemura.com.
Thank you so much, Richard, for taking time to record this interview. Have a great day and stay safe.
Okay, you as well. Thank you so much.
And this is Sanjay Gangal from EDA Cafe.